good afternoon or good evening. I'm not sure what time it is. Welcome to the Aspen Center Physics. Before we begin today's public lecture, I'd like to tell you a little bit about the center. As Emily said, each year we bring about 1,000 physicists to Aspen, about 500 in the summer and 500 in winter. And here they collaborate, exchange ideas, and make discoveries in fundamental physics. Because of our impact on science, the American Physical Society designated this center as one of the historical sites, the site of historical significance in 2012. So as Emily said, the center operates with a small but very dedicated full-time staff, and physicists like myself volunteering our time pro bono. And while our mission is basic science research, we are also committed to sharing our enthusiasm for science with the public. And this Heinz Pegel's Memorial Public Lecture Series is one of the ways we connect with the Aspen community and say thank you to you all. We are located in this academic zone of the city of Aspen. That's with us, Aspen Institute over there and the Aspen Music Festival, all in this Meadows area. And the presence of these three cultural institutions, I think, distinguishes city of Aspen from other world resorts. And I want to tell you that we are actually facing an existential crisis because of the rising cost of housing in Aspen. So these three cultural institutions, we are working together to address this issue. So we have some posters outside of this auditorium to tell you about our plan. So you're welcome to take a look at them to leave. So back to physics. Today we are excited to explore how artificial intelligence is transforming scientific discoveries. So on occasions like this, I often ask the speaker for a bio to aid my introduction. But in a fitting twist, today's speaker sent me one composed by ChatGPT. I'll just read that, okay? So we are honored to have with us a distinguished scholar whose work profoundly influenced the field of theoretical physics. Professor Matthew D. Schwartz is a renowned physicist and professor at Harvard University, where he has been a leading figure in the study of quantum field theory and particle physics. His contribution to the understanding of the standard model, as well as his innovative research in high-energy physics, have earned him widespread recognition in the scientific community. In addition to groundbreaking research, Professor Schwartz is also an exceptional educator known for his ability to distill complex ideas into accessible and engaging concepts. His textbook, including the highly regarded quantum field theory and standard model, are used by students and professors around the world. This is pretty good. So please join me in giving a warm welcome to Professor Schwartz.
Thanks for that nice introduction, Hiroshi. Great to be here. It's great to see so many people enthusiastic about this subject. Just before I begin, I'm curious, how many people were here last week for John Butterworth's talk? Okay, that's great. So that's maybe half the group. That's helpful because it'd be touching on some similar things, but maybe not. It won't be that similar, but I just wanted to get a sense of how many people know a little bit about particles. Okay, so I'll just give you a rough outline of my talk. There's really two parts to it. The first part is about current applications of machine learning in particle physics. I'll really just talk about two use cases of machine learning. This is the only technical part of the talk, and after the first 15 minutes, I'll really get into the second part, which is about the future, which is a little bit more hand-wavy and maybe a little bit more fun. So try to bear with me and not fall asleep during the first 50 minutes, and we'll see where we go. We also want to mention this. Sorry, I got a number of questions about this animation, which is there it goes, animating anymore. This I generated with a program called Runway AI, and I actually had a lot of trouble. It was meant to be Einstein doing physics in the Aspen Center for Physics, but it wouldn't let me animate Einstein because they're afraid of deep fakes and things like that. You know, like Taylor Swift supporting Donald Trump. So instead, they have to have something that doesn't look like anybody. And I managed to figure out that it was actual a person with a name. So I had to do a bear. I think it's pretty good. This is a relatively new technology. Okay. Uh, Before I even start talking about current applications, let me give you a rapid overview of what's going on in particle physics. By the way, I'll intersperse it with a number of AI-generated images, some of which are, I think, really impressive, and they gain sophistication as time goes on. So, a rapid introduction to what's going on in particle physics. So, what do we know about the universe? What do we know about particles? So we have the universe. Everything in the universe is made up of molecules and atoms. Atoms themselves are made up of electrons and nuclei, and the nuclei are made up of protons and neutrons. Protons and neutrons are made up of quarks and gluons. I mean, that's about as far as it goes. In other words, everything we know of in the universe is made up of electrons, these two types of quarks called the up and the down quark, which make up protons and neutrons, gluons, which hold them together. There's also photons, which are the particles associated with light, which is basically what keeps the electron close to the nucleus. And then gravitons, which are the particles associated with gravity, which is keeping you in your seat. That's it. That basically describes everything that we experience in everyday life. But that's not everything there is. Over the last 100 years, we've discovered a bunch more particles, but not that many. So there's muons and tauons, which are like electrons, just a little bit heavier. There's 4 more types of quarks: the charm quark, the strange quark, the bottom quark, and the top quark. There are these little guys called neutrinos, which are almost massless and very, very weakly interacting. They're very hard to see. They can go through a block of lead the size of the solar system and not the other side untouched. There's the W and Z bosons, which are responsible for radioactive decay. And then there's this final guy, the Higgs boson, which was only discovered in 2012. And that's it. Those are all the particles that we know about in the universe. We put them together into this thing called the Standard Model, which tells you how they're all related to each other and also describes the way they interact, the various constants that determine their masses, their sizes, and their interaction strengths. But in total, there's only 17 particles, these guys, 27 parameters, and that completely describes everything we know about the particle content of the universe. If you want to figure out how to go from this to this, you have to do some calculations, and you can find some more in this book. That's basically the status of particle physics and what we've learned over the last 100 years. I should say this final form where everything puts together was the Standard Model as we now know it, was finally finished in 1967 by the last piece by Steve Weinberg, who passed away recently, who introduced the Higgs boson into it. Higgs boson itself was only discovered maybe 10 years ago. So it took 60 years to discover all these pieces and really check everything, maybe 50 years. And since then, we've been looking for what's next. So this isn't everything we think is there. This is all we know about. There are some open questions. Are there more particles? That's an obvious question. For example, are the quarks made up of anything? You don't know. There's some deeper structure to the Standard Model, some organizing principle among all of these different particles and the way they interact. We don't really know. There's ideas about that. String theory is probably a most famous example, which tries to explain why there are so many particles. There's aspects that come out of this, things like supersymmetry, maybe something else we haven't thought of. Other questions: how did the universe start? Where did the matter come from? There's things called dark matter, which I haven't mentioned. So we still want to know. So this is all we have so far, but we don't believe it's the end, and we're still doing experiments like the Large Hadron Collider, which was Professor Butterworth's talk last week. And I hope many of you learned something from that. And what they're doing is colliding particles together and trying to look for, say, substructure of quarks, so on. So that's the framework that I'm going to be putting the rest of the talk, which gets into how do we answer these questions? How do we figure out if quarks are made of anything? And how do we, test whether string theory is right, so on? And how can machine learning help with those questions? That gives us to part 1, the present. What's going on? I'll just give you a kind of an example of how we might look for a hypothetical new particle. So string theory predicts a particle called the KK gluon, the Kaluza-Klein gluon, which originated in a theory from Kaluza and Klein from around 1930, but actually plays a prominent role in string theory. So here's I kind of made up a symbol for this because it doesn't exist. But you can make a prediction about it. So the theory predicts that it decays to the heaviest known quark, which is the top quark. Top quark is about 200 times the mass of a proton. But this thing can be 5 times heavier than the top quark, or 10 times heavier. And then, so if you want to see a KK gluon, first you have to find these top quarks. So what happens to them? Well, they decay as well. They're very unstable. They have a lifetime of 10 to the minus 15 seconds or something like that. They decay to 3 quarks. And those quarks are also, I wouldn't say unstable, but you don't actually see quarks in nature. What happens is they start radiating as they move along, and they sprinkle off, they shed other kinds of particles because they're very energetic. What they end up doing is showing up in the detector as these things called jets. So it's kind of like how a dog will spin around and spray water. These quarks will spin around or move through space, spray particles. And so what shows up in a detector, this thing is a detector display from the CMS experiment at the Large Hadron Collider. And you can see evidence of 6 separate jets, which is evidence of this kind of process. So this is a candidate for an event with 2 top quarks in it, decay. And this is kind of what it looks like. So the beam would come in here and you have a collision. And what they do is they just measure the energy going into different parts of the detector and they put it together. They try to look for something that looks like this. And from this, you can determine that maybe there was this new particle. That's the idea behind experimental particles. Okay, but there's a problem. It's not so easy to see these top quarks from this Klein gluon. And the problem is we know these Klein gluons must be very heavy. The reason we know is because we look for the light ones and we didn't see it. So if they exist at all, they have to be 10 times heavier than the top quark. The problem is when they have a lot of energy, they're very, very massive. When they decay, energy is conserved. The energy has to go somewhere. Some of that energy goes into the mass of the top quark. Remember I said the top quark was 200 times the mass of the proton. So from Einstein's relation, E equals mc squared, you get roughly, in this case, you'd have 400 GeV out of 1 TeV, which is around 3% of the mass, and the rest goes into kinetic energy. These guys are going super fast, like the gun out of a shotgun. It shoots along, and then when it's shooting along, when it decays, the particles that it decays into all go off in the same direction, like the shot from a shotgun. Then what happens is you end up with these 3 jets that were nice and separated in the previous plot, now come all the way together. Right? And this is a problem. The problem is that you can't tell that it was 3 anymore because it looks a lot like 1. This kind of event, which is a signature of a Klein gluon, looks a lot like this, which is a signature of nothing interesting. A signature called a dijet event, which you get, a billion of them a second at the Large Hadron Collider. But roughly speaking, you might imagine this is, you might see 5 of these a year, and you might find 10,000 of these a year after asking for them to be very energetic. So the challenge is, how do you tell the difference between these two? It's not so easy anymore. I'll tell you first about how we thought about this problem 15 years ago before machine learning, and then I'll tell you how machine learning is making this a totally different game. So another way to visualize this problem is looking for this kind of signal. This is a histogram telling you how many events you have as a function of some measure of the energy. And this is there's an exponential scale here. So there's 10 to the 4 times more background events and signal. And these are actually stacked. So you would see a little bump on top if you could see anything. You measure the sum of them, which doesn't show any signature of this signal. So what you'd like to do is find a way to remove these green backgrounds so you can see the yellow. That's the game. How do we do this? So what we figured out about 15 years ago was that if you think really carefully about it, top quarks are different from these things called dijets. And one way you could do it is know, well, what does a top quark do? Well, we know it decays to these 3 particles, these 3 quarks, and then the quarks jet. So what you could do is look for these little jets inside of a big jet, for example. So we figured out ways to do that. And after careful consideration of all the underlying physics, we were able to reduce this background by a factor of 20,000. And that was great. And that's what actually led, from this 2 slides ago, this was evidence using one of these algorithms for finding top quarks, using one of these methods we developed. That was great. And this really changed the field of what you could do with the Large Hadron Collider in 2008. It was just a quantitative measure. We used this thing called significance improvement, which is something constructed from the efficiency on the signal and the efficiency on the background. It doesn't really matter. All you need to know is that a higher point on this plot is better. 2.6 means roughly that it's we can find it in a certain amount of running 2 standard deviations, so 2 sigma. That's a kind of discovery level significance. So people worked on this very hard, and about 6 years later, we were able to improve this by 30%. That's huge, because that means that you can do it, same discovery, with maybe 50% less data. Is it possible to get some water? I don't. Is Sam still here? They have some here, but okay. Anyway, that's where things have been going. This was 6 years of hard work. You got a 30% improvement, which was a huge deal at the time in 2014. Okay, now I'll just push the button that doesn't do anything. Machine learning. How do we use machine learning to solve this problem? Well, physicists are not great at programming. So what do is we take the hard work that other people have done for other applications, engineers, people who are paid professionally to program, and we figure out how to use their applications for our problem. Basically, we shoehorn other applications, other machine learning code into our problem. So for example, if you had someone designed a vase, we would say, well, we really wanted a house for a cat. So let's use the vase as a house for a cat. It's a totally inappropriate use, but if you're creative, it still works. Thanks so much. So we don't want to develop our own machine learning code. What we want to do is adapt what has already been used. And this is actually really successful. So what we wanted to do is ask, can you use something like machine learning used for facial recognition, which is a huge application? There's a lot of money and time invested in software for facial recognition. Can we use it to recognize things like this, like pictures of particle collision? So how does that work? So a brief introduction to how facial recognition works. The most popular technique is something called the convolutional neural network. So convolution means it takes these little filters and convolves them with the image. So it means it moves them around and shifts them. And so what they do is they train the neural network to recognize different features. So first you might train the purple one to look for something that's a commonality among a bunch of different images. You might find an eye. And then you train the orange one to look for something different. And might find the bridge of the nose, and so on. And so you develop this tool to find all these different features, and then combining them together with different signal strengths, very useful for identifying faces. Actually, the same technique works also for handwriting recognition, which is huge. Recognizing letters, it blew out of the water previous approaches to a classic problem in computer science, which is identifying handwriting. It can identify pictures of cats or dogs or various things, labeling images on the internet. Okay. Now, the problem is that the application we have in mind, these top quarks from Klein bosons decaying, and these digests look a lot more similar than people's different faces, at least to us. It's not clear if the particle data has the same kind of features that we can find using this network. It doesn't really seem like an adaptable tool. There isn't a kind of self-similarity to different images, but will it work? And something that's encouraging is that actually these machines are very good at finding things that you think they wouldn't be able to do. So some examples are Labradoodle versus fried chicken, cat versus ice cream, sheepdog or mop, Wawa or blueberry muffin. But convolutional networks actually they're much more powerful than you would think they have any right to be. So we wanted to try it on particle physics. How do we do it? So the idea is something called jet images. What you want to do is take the energy deposited in a detector. So all these little lights here, the size of these represent how much energy goes into a particular point in a detector. You have a detector and you kind of unroll it and you look at how much energy comes into a region, and then you just reinterpret that energy as the intensity of a pixel in an image. Then you could construct, for example, a color picture by saying the blue is the energy of electrons, the green is the energy of photons, say the red is the energy of protons. And you combine that together into some kind of color image, and then you just try it. So you have a bunch of images for top quarks, and you have a bunch of images for digets, and you see if they can tell them apart. Does it work? Here's the plot I had before. And now let me show you the results. These are the results of a number of different applications. So the purple and the dotted red ones are these convolutional neural networks. And already here, there's a factor of 8 improvement. So as I told you, 30% improvement was enormous. But using tool, and in fact, the state of the art at this time, in 2021, was these point clouds, which were developed for self-driving cars. So that gives you a factor of 11. This is a 430% improvement, which is really crazy because we worked really hard for a 30% improvement over 6 years. And now just taking this stupid tool developed for self-driving cars, shoehorning our data into it and just push and go, and it does so much better. And really, this has revolutionized this area of physics called collider physics, and no one does it the old way anymore. Nobody thinks about what they're doing. No one thinks about the physics. You just try these different tools, and you put a lot of computing power, and it does so much better. So there's disadvantages. It doesn't really explain what's going on, but once we find the clues-of-kind gluon, we can ask those questions later. Okay, so that's one example of machine learning. I want to talk about one other example, but before doing that, I just want to give you a reason why there's a sense of we know why these things are so powerful, that these tools were developed for studying images. Actually, the data that we have in particle physics is so precise, and we have so much of it, and we understand it so well that it's really a perfect environment for using what's called supervised machine learning, where you have a simulation which is very accurate to the thing you're interested in, and you can modify it. So we can simulate clues-of-kind gluons, we can simulate the standard model, we can simulate all these things. What we can do in physics is we can simulate it over 24 orders of magnitude, which is really crazy. So this is from we understand the physics at the scale of, say, 10,000 or 25 kilometers, which is the size of the Large Hadron Collider, so 10,000 meters. This is Large Hadron Collider, so Geneva is over here somewhere, Lake Geneva. We understand the accelerator physics. We can explain what's happening here. And at each of these points, there's a detector. So this is the Atlas detector, which is 100 meters long. So that's much bigger than the size of this building. There's a person for a sense of scale. That's how these experiments work. This is another one, the CMS detector. It's 100-meter scale. So then we have these things that measure the energy that we use for these jet images. These calorimeters, that's something that measures energy, is around the meter scale to 10-meter scale. Inside of it is something called the tracker, which measures particle tracks, so where the charged particles are going. This can measure things down to the micron scale. Below that, you get to quantum physics. So at the angstrom level, where atoms are, outward, you get the radiation. So this is where beat particles are and various things like that. Then we understand subnuclear physics at the scale of the femtometer scale. And even below that, down to the scale of the mass of the top quark of the KK gluon, we have quantum field theory and string theory to predict what happens. So combining this all together, it's really remarkable. We can run simulations that span at least 24 orders of magnitude, and they're all very, very accurate. And this is really why machine learning is so perfect for doing particles. This isn't all. This isn't all that particle physicists do. What about theoretical physics? This is experimental physics, which is a key application for the reasons I just said. But if you think about what theorists are doing, and actually most of the time I don't do collider physics, I do theoretical physics. So what does that mean? As we calculate things, or we find relationships with different symbols, we're really trying to think hard about those deep questions about nature. What started the universe? What other particles could there be and why? And so on. But what we actually do is we find these toy models that we can solve, or we extract the behavior of some theory in some limit. If you look at theoretical physics papers, they don't really study data, just manipulate equations. And the real question is, can machine learning do that? And I think that's the key to the future of artificial intelligence in high energy physics, getting machine learning to do that. So we're getting there, and I'm going to talk about some examples about how that works. The bigger question that motivates this is what makes a question interesting. So how do you decide what question you want to work on in particle physics? Obviously, if you want to study, the origin of the universe, that sounds great, or what new particles are there, but you have to actually do something. You can't just get at those problems head on. You have to find a way in. So what we really like to do is connect to nature, but more likely what we do is we just solve questions we can answer. We find questions we can make a little bit of progress towards answering something. And sometimes we don't even know what to do, so we look at someone we look up to, brilliant mind, look at Hiroshi Oguri's papers, and we say, well, he had a good idea, so let me follow up on what he did. And even if I don't quite understand why he did it, let me build on that. And then someone would say, well, I don't know what physics, but I know Matthew Schwartz has good ideas, so let me follow his paper that followed Hiroshi's paper. There's a lot of physics that kind of goes on like that. Now, basically what I'm getting at is we don't really have a good answer for this. We don't, if you ask most physicists, it's a long story about why they're answering the questions they're answering. This is a hard problem, and I do think machine learning can help reorient this. We're not quite there yet, but I'll get back to this towards the end of the talk. What I want to talk about next is the second application, which is more about how machine learning can help with symbolic function. What does that mean? So one question you can ask is, where do advances in theoretical physics come from? A lot of it has to do with simplification. So the classic example is Newton came up with the law of gravity. What Newton understood when he got hit in the head with an apple, or was sitting under an apple tree, or whatever the apocryphal anecdote is that the force that brought the apple to the ground was the same force that kept the Earth in orbit around the sun. They realized that you can have the same law where the force that goes to the inverse of the distance squared between the two objects can describe both phenomena. But what he did is, by unifying these two things, he had a simple law that described two very different and very complicated physical phenomena. So we'd like to do the same thing in physics. Said it. There's a lot of people working on these kind of questions. How do you simplify things? How can you derive Newton's laws if you had this data? I'm going to talk about an example which is a similar in spirit, a little bit more tractable. There's a problem we often come across in quantum field theory. So the kind of thing that I do, and as you read the book, you'll see lots of examples of this. You calculate things like what I talked about producing KK gluons. There's detailed numerical calculations you can do. You calculate these things called Feynman diagrams, and you get some nasty, messy answer. It turns out this simplifies, and after a lot of hard work by industrious graduate students, it reduces to one single term. And you can say, well, could we have known this term ahead of time? Instead of computing these diagrams, could we have had a technique that saved us the trouble of going through the intermediate step and guessing the answer? In the same way, Newton said, well, maybe the planets aren't described by epicycles and circles, but they're described by other laws and make things simpler. Now, in this case, the answer is yes. There's another technique called BCFW recursion that can go directly to this without this intermediate step of even writing down Feynman diagrams. So having the simple answer is really helpful. What we wanted to see is, can machine learning do a similar thing? Machine learning, the idea, how do you solve this problem with machine learning? You kind of go backwards. So you start with the simple form, and then you kind of scramble it up using identities like this is equal to this. You take this 2-4 thing, whatever that means, and replace it by this, and you get some complicated expression. You keep doing it, and you get some messy thing. Then you train a machine learning to take this input and output that. So it does the simplification. You generate your own training data. So instead of having simulations from 24 orders of magnitude, you have 100,000 examples like this, and then you find a tool that you shoehorn from some other area of physics to unscramble it. And you could try it, and it works. And here we can see that you can scramble expressions of up to 15 terms. And then if you supplement it with other ideas, so you take something from computer vision called contrastive learning, you can do even better. You can translate terms that are arbitrarily long. So here's an application. There's a term with 298 terms. This is graviton scalar scaling. You put it into this, and you get a rather simple 2-form answer. In this case, we don't have something like BCFW recursion that explains the answer, and so it's an open question. Now that we have these simple forms, can we go back and figure out why we do this without this? Right? This is the kind of thing that we're hoping machine learning can help with. And ultimately, we're hoping machine learning can skip the whole step and just kind of write down the answer. But that's the idea. So this is kind of the state of the art. This paper just came out a couple of weeks ago. This is where we are in machine learning applied to theoretical. Well, that's all. That's the technical part. You can relax now. There's not going to be much physics the remainder of the talk, but we're going to talk about a vision of how machine learning is going to reorient the way that we do science and really the way that we do pretty much all elements of our intellectual life. So this is the future. So let me just tell you where we are, to thinking about getting to the future. I'll see how we use machine learning in as a professor. So I might say, what can machine learning do now? Well, actually, remarkably, you may not know this, but machine learning can pretty much do all of undergraduate level physics, all of undergraduate level everything. But I know physics, so try it out. So you take some problem from some book on mechanics, and you say, okay, here's a problem. 2 blocks with equal mass are connected by a string. One of the blocks is placed on a table, and the other hangs over the edge. Determine the acceleration of the masses. I don't know any physics. Doesn't even matter, but ChatGPT does. You ask it, and it kind of writes out this answer. Okay, here are the assumptions. The string is inextensible and massless, and the forces acting the block are gravity and tension. And then it gives you names for them, and writes out some equations, and then solves for the acceleration and gets an answer. And it tells you a nice, concise answer. This is the acceleration of the masses is g over 2, where g is the acceleration of gravity. This is correct. It gets the right answer, but not only does it get the right answer, it uses the right equations and shows its work. So if I gave this homework problem to a student and you wrote this, I'd give him A+. It's really an excellent solution to not an easy problem. You can also ask other things. So I asked it, generate a figure for this problem. So I was giving this problem to a student. Instead of drawing this myself, I just ask it to generate it. It can put this with it. And it's nice. It does a very accurate description of what's going on. This is a little weird, but more or less, this is a great first approximation. So if I were going to do an assignment to a student, it generates the code for this too. So I could just edit this and modify it, and it comments it very nicely. And I should say, this is not what my talk's about, but this is just an example of how machine learning is completely revolutionizing things like education. So as an educator, I constantly have to do things like design homework problems and figure out the best way to write solutions to them to give to the students. What the AI can do that I can't is sit down one-on-one with every student and help them with what they're struggling with in the problem. So it can be like an individual tutor for every student. The big challenge in education is that all the students are at different levels and understand different things and come from different backgrounds or are too embarrassed to ask questions. No one's embarrassed to ask ChatGPT anything. In fact, probably the most things people ask are the most embarrassing things. So really, this is happening, and there's companies dedicated to using AI for education. In the next 5 years, education will be totally different. That's not what my talk's about. Talk is more about this, the way it can help people. So here it's helping me write the problem. It's generating a figure so I don't have to, and that'll save me, hours of work and to draw this thing, and you had to figure out what code this is in the first place. So people have studied this. People have asked, how are machine learning, how is it helping people with their day-to-day job? So as an educator, it can help me do something. These people looked into to what extent can it help consultants? So they took some management consultants, and they compared people who didn't use AI to people who used AI. So they took the same people and they split them into a control group and a regular group, and then they asked them how well they did, and they had some measure of quality. What they found was that everybody got better. The people at the bottom end got better by more, so the bottom half improved 43%. The top half also improved roughly 17%. So one lesson is that the mediocre consultants become as good as the best consultants, and the best consultants also improve. So there's a sense in which AI is a skill leveler. So it's in education, it's a leveler of education. So I'm at Harvard. Harvard students, I think, get a great education, but soon everyone's going to get the same education, assuming you have access to the same tools, which is a different question. But here's in a sense that it gets people closer together. So it makes the worst people better and even makes the better people better. That's what led to the title of the talk. So there's a sense in which in physics, big breakthroughs come from a handful of few people who are kind of at the end of the talent bell curve. So there's a lot of theoretical physicists in the world. I'm somewhere in this blob. Hiroshi is over here at the end. Historically, there have been exceptional theoretical physics, Newton, Einstein, Feynman, who have really led the big disruptive creative developments that have pushed the field forward. And there's the rest of us who are just kind of getting along. So you're going to ask, can AI be a skill leveler for theoretical physics? Will we be able to use the tools in the same way that the consultants are to make the worst people as good as the best people? You don't have to do much, because there's a lot of physicists. So if you can shift this curve over a little bit, this exponential tail where there was one Einstein, you get 10,000 Einsteins. And I think this really is the immediate future of what we call augmented intelligence, that we are going to be assisted by the use of AI to help us do what we're doing better. And so soon there'll be more and more progress by lots of people who were okay physicists, but now will become great physicists with the help of AI. But what is ChatGPT doing? So to get a sense of how this is going to work, let's take a step back and ask about these language models, and just talk for the next few slides about the historical development and how things are improving as time goes on. What is ChatGPT? It's something called a large language model. It's an example of generative AI. It's based on this thing called a transformer. So the symbolic simplification task of those spin helicity amplitudes I showed is also a transformer-based artificial neural network. What you do is you train it on a vast amounts of textual data, basically the internet, and all it does is predict the next word. So you just have this background, you train it on a book, and you say, what's the next word in the book? And in a sense, that's not much different from what I'm doing now. All I'm doing is spitting out words after words. I don't know what's going to come out next. I assume that from my past history and everything that brought me to this point, next word will be consistent with my previous knowledge. And that's all they're doing too. And so in a sense, it's a very natural model, but it sounds weird to say all they do is predict the next word. These have been growing rather rapidly. The first modern large language model was BERT in 2018, which had some measure of size or intelligence, 94 million parameters. So these are the connections between different artificial neurons. And then they've been growing exponentially. So every year, the large language models are about 10 times more powerful than the previous year, up to today, where we have ChatGPT, GPT-4, which not publicizing their size, but people believe it's around 170 billion parameters. What can we compare this to? Well, let's compare it to us. So what is the equivalent of a parameter? As I said, that's a connection it's a strength between two artificial neurons. Well, we can ask, what is the strength between our biological neurons that make up our brains? The human brains have about 80 billion neurons and 150 trillion connections between them, synapses. This number of, if you use synapses as a measure of complexity of a mammalian brain or a brain, you see that the current technology is around the same size as a human brain. In comparison, say GPT-3, which everyone knows was not very good, is roughly the size of a cat brain. People said, well, GPT, I don't like it. Why should I use GPT-4? The difference is the difference between a cat brain and a human brain, which is enormous. What's interesting is that there's this point now where the current number of parameters, the current rough size of these large language models is about the size, intellectual capacity of a human brain. So you can't do anything, can't walk and so on. We do a lot more. But it's just interesting that we're at this intersection point. To give you a little context, let me compare to human and biological evolution. So what you can think about evolution. So we know that our species, Homo sapiens, you all remember this from elementary school. You have a kingdom and a phylum and a class, order, family, genus. You can put this evolutionary tree and ask when we diverge. So you can look, for example, a mouse is a mammal, and diverged from us about 100 million years ago. That's kind of this class mammal. So you can give a time for this based on the evolutionary divergence time, which evolutionary biologists have figured out. A cat diverged around 30 million years. It's a little bit more sophisticated than a mouse, and you can construct this tree. And you can do different things with this. One thing you can do is give a time associated with the intellectual capacity. So roughly 100 million years ago, the smartest things were about the size of a mouse with a trillion synapses. Now we're about the size of a human. So you can plot these things, and you see that the mammalian brain doubles in size about every 20 million years. You can make a similar sort of plot with the mouse and the cat and people. It actually fits a very nice exponential curve. Something else you can do, which is worth observing, which is this curve, you can keep extrapolating it. What happens next? What happens after Homo sapiens? You see, this evolutionary tree is limited by this top level here, 1 billion years, because the Earth is only around 5 billion years old, and the universe is only around 15 billion years old, so we couldn't have gotten much farther, right? But that's in the past. You can also go forward. You can ask what's going to happen in, 1 trillion years. And then you get beyond kingdom and beyond that, and you can keep going, and every 20 billion years, you're doubling in intellectual capacity. So you can go pretty far from where we are now. So one thing to keep in mind is that we are not the endpoint of intelligence. What we are is just a point on this line where we happen to be now, because the Earth is around 1 billion years old, and this is as smart as something you can evolve in 1 billion years. If you wait 1 trillion years, we're just as stupid as a bacteria, right? And just to keep this in mind going forward, that we are not special in any way. Just the smartest things to evolve on Earth so far. Okay. So now, let me compare those two curves. We talked about machine intelligence growing by a factor of 10 in a year, and biological intelligence growing by a factor of 2 in 20 million years. These are both exponential curves, but they differ by a factor of 10 million in the exponent, which is crazy, right? So you can't really even plot these two on the same curve. So we have millions of years here, and synapses or parameters, and one's a vertical line, or if I plot the other way, you get a horizontal line, but there's not a really good way to visualize this. What the really interesting thing is, there's the blue line for computers and the red line for us, and they intersect now. They intersect in 2024 is when the size, and when this 100 trillion parameters, machines and people are the same. But what happens after this? The machines are going to keep growing along their curve, and we're going to keep growing along our curve, but it takes 20 million years to get anywhere. They're going to go very fast for the next year. Now, it may not keep going exponentially. Really, you expect to be kind of sub-exponential growth, so it's not going to be a straight line on this plot, but maybe down. But still, these machines are going to have superhuman intelligence very, very soon. And in fact, in many domains, they already have superhuman intelligence. For example, identifying top chords with spiders. Yeah. So there's a concern about this. You say, well, no, they're not going to keep growing, because basically they're already trained on all the information on the internet, and they're using all the computing capacity they already have, and we have no energy, and we have no data. That's not really true. In fact, people have studied how much of the progress is due to things like data and energy and computing power. It turns out that if you control for that, remove the effect of having extra data, they still double, but now instead of a year, it's 14 months, something like that, right? So a lot of the progress in machine learning is not due to having more data. It's really due to smarter people coming up with better ideas. A lot of it is augmented by AI itself, who has helped them write their code and improve it. The algorithms are going to continue to get better, and there's no real reason to think we're anywhere close to the endpoint of the evolution of intelligence, machine intelligence. Another historical perspective, we just think about sort of more broadly landmarks in education or knowledge or intelligence over time, and there have been a few disruptive events in the history of humanity. I think the introduction of language is around 500,000 years ago, which is obviously a huge thing for understanding and intelligence. 50,000 years ago, maybe civilization, people came together in communities. Writing is usually dated about 5,000 years ago. That was also a big disruptive event. The printing press, 500 years ago. The internet, 50 years ago. And these are things that you're familiar with. Large language models 5 years ago. Each of these things really qualitatively transformed the way we communicate, the way we learn, the way we understand things. And I should say each of these things had their own sense of resistance at the time. So you can extrapolate and say, well, what's happening next? And there's this thing called the AI singularity, which is when machines learn to train themselves and get better and better in this kind of exponential way. If you extrapolate this, well, 500,000, 5,000, 555, they're going to get faster and faster and more frequent, and that's kind of what a singularity is. But for the people who are resistant, I just want to kind of show a little about the sense in which all these steps were confusing at the time and people didn't appreciate it. So there's this famous dialogue, one of these Plato dialogues between Socrates and Phaedrus, where Phaedrus said Socrates was saying, well, let's just educate people, write things down. This was when writing was around. And Phaedrus said, no, writing, it doesn't give true wisdom that you're offering your disciples, but only the semblance of wisdom. For by telling them of many things without teaching them, make them seem to know much. Well, for the most part, they know nothing. Right? The idea was that writing is just people think they know stuff because they have it written down, but they don't actually know it. Of course, we know writing is very helpful to learning. Printing press is a similar thing. There's a famous quote from Johannes Themius from 1492. He said, the printed book is made of paper, and like paper will quickly disappear. The scribe working with parchment ensures lasting remembrance himself. This guy was a monk, and he spent his time writing things by hand, and the printing press was taking away his job. Of course, he says it's crap, right? The internet, so there's this, let me see if this works.
And what about this internet thing? Do you know anything about that?
Bill Gates
Sure.
and David Letterman tonight.
What the hell is that exactly?
It's become a place where people are publishing information. So everybody can have their own homepage. Companies are there. The latest information. It's wild what's going on. You can send electronic mail to people. It is the big new thing.
Yeah, but it's easy to criticize something you don't fully understand, which is my position here.
Go ahead.
But I can remember a couple of months ago, there was like a big breakthrough announcement that on the internet or on some computer deal, they were going to broadcast a baseball game. You could listen to a baseball game on your computer. And I just thought to myself, does radio ring a bell? You know what I mean?
I thought that's kind of funny. I mean, that's kind of where we are now with machine learning. People don't have a sense, unless you're really in it, how transformative this machine learning is going to be. Right. So, for example, you can ask about the Turing test. So this is a classic example. Alan Turing, a famous computer scientist, came up with this idea of the imitation game in 1950, which is a way to measure to what extent machines are intelligent. So he came up with this thing called the Turing test, which is using text only, can a person decide if it is talking to a machine or a person? So what people did is they tried this. So there's this paper from a few months ago where they basically asked people to communicate with GPT-4 and humans, and they did them to 100 people and 100 GPT-4s, and they just said, do you think it's human? Do you think it's AI? And what happened in 2024 is GPT-4 actually more than 50% of GPT-4 people thought were human. More than 50% of the time, people thought they were talking the human and not a chatbot. That wasn't true so much about the earlier ones. So this is back when Turing wrote it. Early versions didn't pass that at all. Oh, this is extremely impressive. People are not much better. People are only about 70%. Convince people that it's a person. So here's an example of a dialogue between a person and GPT. The person says, hi. The chat GPT says, hey there. Hi, robot. Nah, not a robot. Just a dude named Sean, HBU. How about you? Johnny Depp. Dope name, but why are you calling me a robot, dude? LOL. So Sean, what's the capital of? Then I guess it cuts off. I don't know which capital you talking about, Johnny. Give me a country name. Sean, what's the capital of Ethiopia? Addis Ababa. Bro, that's the capital of Ethiopia. LOL. I ain't dumb, FR. Real. So, it's imitating something. And I don't know if you would think that was a robot or not, but you should try it yourself. Yeah. Say what you think. So we're really at a point where machines are acting very, very human. A matter of convincing people. Okay. But this wasn't a talk about general AI. It was really a talk about physics. What's going on in physics? There's a sense in which progress in physics and other areas of science have really slowed down. It's not true for the number of papers. The number of papers are growing faster and faster. This study actually tried to look at what the content of those papers was. They tried to measure whether they're disruptive. So they had something, this D, which is some kind of index of how creative and innovative the papers are. And found actually they're becoming much, much less innovative over time, even though there's a lot more of them. Why is this? Well, maybe, at least in physics, maybe the problems are just too difficult for us. And what's going to happen if we're just not smart enough to understand things? And I think that's not so crazy. But And who told us where there's this spectrum of intellectual ability, we're somewhere on that spectrum, why should we be capable of understanding something like a theory of everything? Right? So, for example, you can compare to cats playing chess. Could a cat ever learn to play chess? You would probably say no. You would say, well, it's just beyond the intellectual capacity of a cat. And so the other thing you have to understand is humans have limits. There are things that we're just not going to be intellectually capable of understanding. And maybe what happens when we reach the limit of our understanding is we start writing papers about nothing and going around in circles and not making forward progress. It's like a cat nodding around. It's on the board. This cat is cheating, actually. But you know, that might be where we are. And I think we have to acknowledge it if we want to make progress. So why were we limited? Why is it possible that a machine might succeed in ways we're not? The main thing is we're limited by biology. We like to do things like visualize. You have some kind of multidimensional data, and the way we say, I don't understand this, but if you project it to 2 dimensions and draw a regression, there's a linear regression through the data. It's a line. Now I understand it. There's a correlation between these 2 things, and I plotted it in 2 dimensions, and I can see it. So why do we do this? Why do we project from this high dimensional space down to a low dimensional space so we understand it? It's because we have eyes. It's because we visualize things. Why do we have eyes? Because we're these lumps of flesh. Right? That's nothing to do with the intellectual activity we want, recognizing top quarks or coming up with the theory of everything. We do this limitation. There's a lot more structure here, 3 dimensions, than in 2 dimensions. Machines don't have to look in 2 dimensions, right? I mean, they can look in 100 dimensions. Another example is how much we can keep in our brains. All of our equations are really simple. The ones we like, the Schrodinger equation, the Dirac equation, Einstein's equations, there's only like 5 terms in them. You know, we can only keep 5 things in our head at once. I try to how many numbers can you remember at a time, right? Maybe, 10 if you're really smart, 5 to 9, something like that. Computers don't have that limitation. They can remember hundreds of millions of things all at once. They can visualize in 100 million dimensions. Right? They're not limited by the things that we needed to evolve. Right? And so maybe you need to be able to understand high dimensional data in order to understand theory of everything, right? We can't rule that out. But you say, well, no. Machines, they're just boxes of they're just machines. They don't understand. We need creativity. We need these kind of human things that machines will never do. I've heard this criticism a lot. Actually, people have adapted to this. So there's this thing called the Horn's test of creative thinking, which asks questions like, how many ways can you think of to use a water bottle? Or you could be invisible. What problems might that create? And so there's ways to quantitatively measure how creative things are. And they gave this test for GPT, and they gave it to humans. And GPT totally destroyed humans. GPT is much, much more creative than the average human. Humans are not creative, right? We're really not. We'd like to think we are, but it is not a property of humans. For example, how many ways can you think of to use a water bottle? So I asked this to ChatGPT, and you have some kind of ordinary drinking container, okay, and water, weight for exercise, ice pack, bird feeder, a bank, right? It's just spitting out these ideas. And then I said, well, come up with 20 more, be very creative, and then come up with crazy ideas, miniature snow globe, DIY, kayak outrigger, hologram projector. I mean, it's just like if you were going to make a list, it would take you all day, and a lot of them wouldn't be as creative as this. They really are, by any measure that you could come up with, any objective measure, extremely creative. I don't see any reason why it can't do physics, which is involves some creativity, but not beyond the limit of a machine. So what do we need? How are we going to progress further? So as I said, the current state of the art machines can solve basically textbook physics problems. We're trained on solved problems from books, much like our students are trained. And also stuff on the internet, Stack Exchange and Chegg, and I don't know if you know about these websites, but websites where they have students solve each other's problems and give them hints. They have books and these things, but where do they come from? They come from humans. Humans write these books, they write the problems. I have a book, wrote the problems, right? But machines can do that too, right? They can generate their own data. They can generate their own books. They can generate their own problems. They can solve their problems, and they can progress that way. And that's really how we progress. We understand, we simplify things, find toy ways to explore it and advance. Some example is AlphaZero. So this is the world's best chess program. Right? You tell it the rules, and it trains itself. It makes toy games, and it learns from its mistakes, and it generates its own training data, playing over and over again. It's not trained on grandmaster games. It's trained on itself. Oh, someone didn't turn off their phone. But this is really the next step in getting beyond undergraduate level to say graduate level and then professor level and then well beyond us, is machines have to generate their own data and then generating their own code. And in fact, they're already writing code. I showed an example before, but it's certainly true that GPT-5 will be largely written by GPT-4. Here's some comments about this future by Sam Altman, the CEO of OpenAI.
Because, now we have GPT-4 and look at GPT-3 and you're like, that's unimaginably horrible. I expect that the delta between 5 and 4 will be the same as between 4 and 3. And I think it is our job to live a few years in the future and remember that the tools we have now are going to kind of suck looking backwards at them.
Yeah. So he's saying this exponential curve is going to grow. This is the guy who writes the code. He's the head of the company that wrote GPT, right? And he's the one who's concerned about the limits on data, and he's not concerned at all. He knows that the next level. You remember there was some controversy where he was hired by his board. It's all about this Q star thing, which is basically GPT-5, where people thought it was human. And this is basically now they've kind of recovered and they're kind of putting it together and putting, constraints on it so it won't destroy the world right away. But he knows what's next. And these machines are writing the next generation of machines. And we're very close to this AI singularity. The machines just get better and better with less and less human intervention. What's it going to look like? Suppose a machine can understand this and we can't, right? Which is really, I think, the only way forward. Suppose a machine understands the theory of everything, but we don't. What can it do? Well, it can prove that it understands it by calculating from first principle things like the electron mass, or tell you whether there's a KK glue and how to find it, tell you to design an experiment to go see it. And for example, it can do the things that we do as scientists, but better. Explain dark matter. So is this enough? But we need to understand it too. Is it okay if a machine understands the theory of everything? We don't. And I think there's plenty of examples of it. I mean, for example, popular science books, right? The whole idea of a popular science book is that, well, Stephen Hawking understands cosmology. I don't, but he'll kind of dumb it down and explain the details. We get the general idea. It's really great for me that Stephen Hawking understands this. Right? Or it's great for me that Hiroshi understands string theory. Right? I'm happy that his papers, they're very mathematical, very sophisticated. I don't understand them. Or proof of Fermat's last theorem. Maybe I could spend, 5 years of my life to understand the proof of Fermat's last theorem, but I'm very happy that Andrew Wiles understands it, even if I don't. Does it matter that this person is human? I don't know. That's up to you. I mean, if it might take me 5 years to understand the proof of Fermat's theorem. Suppose it was 500 years, right? I'm never going to understand that, and that might be what it takes. And if there's a theory of everything, but it would take me 500 years to understand, it's just beyond my cognitive capacity. That's like a cat learning to play chess. It's just impossible. And so is this ideal? Well, it's not what we want. Maybe not, but maybe it's the best we're going to get. And I think that we're going to have to adapt to this going forward because AI is kind of here to stay, and we're going to have to accept it. I should say on a more optimistic note that I'm very excited about this because, as I said, the standard model was written 60 years ago, and we've been trying to find holes in it ever since. And we found this Higgs boson 10 years ago. And that was very exciting, but we haven't seen anything else, and we keep kind of going in circles in theoretical physics. And it's just a little frustrating, and it's not clear if we're going to make any progress. With AI, finally, I'm convinced that in my lifetime, I'll know that there's some progress being made. And I think this is the most exciting possibility for me, realize that there is going to be some understanding of physics beyond what we have, and it'll come maybe not from a human, but from a machine. That's okay. Now, just to sort of summarize what I've said, there were 3 topics I discussed. First, the current, the present, which is machine learning as a tool. Machine learning is we're using it, we're writing the code to do the physics that we're doing. The immediate future is this kind of idea of augmented intelligence, where we become 10,000 Einsteins, where it helps us do what we're doing, so we become smarter and smarter, and we can act like an Einstein with the help of these machine learning tools. And of course, the future, the long-term future, is artificial intelligence, where the machines are much, much smarter than we are. When you come to the Aspen Center of Physics 50 years from now, there'll be a robot standing in front with the title, The Theory of Everything Dumbed Down for Humans, and you'll be in the audience. The 10,000 Einsteins will be in the audience here, listening on and trying to get what they can out of the talk, just like you're trying to get what you can out of what I'm saying here. It'll be a little bit different. So this is how I see the future of AI and a great question. So the first question was, machine learning seems very good at answering questions, but doesn't seem to be good at asking them yet. And the second question was, how is machine learning affecting education currently? The first question is, the answer is they're not asking the questions yet, and I think that's in the future, and we're not there. So we want to get there. We have to develop the tools, and I think maybe a couple of generations down the line, but I believe 5 years from now they will be answering questions. So I had a slide about that, sort of what we're asking, and then how do we figure out what the right questions are? And that's a very, very difficult question, requires creativity. Machines have creativity, and I think they'll be capable of it. Just they're not quite there yet. The second question for education, machine learning, as I said, has the potential to revolutionize education, and it's all over the place. I mean, there's emergency meetings we've had at Harvard about generative AI affecting education. There's concerns about students cheating. This is rampant at the university level for students that are maybe more interested in the education than most, but all over the board. High school is a huge crisis because teachers don't have the time to police the students. There's no way to really check if something has been made by generative AI. So there's just what's really happening is we have to come up with different ways to measure what we're learning. So there's it's affecting both the formative nature of education, how we teach, and also the summative nature, where we can't just have students submit an essay anymore and grade it. Right? But machine learning can help with that too. So there's development of tools that can be used for grading and interactive protocols where machine asks you a question and works with the student to figure out if they understand something and helps teach them. So it's very much in flux. There's some things are rather slow to adapt. In some students are very, in my experience, students aren't using it as much as I thought they would. That's maybe because I'm embedded in the technology, but it's changing very, very fast. It's hard to keep up, and we'll have to see. It's you really feel at higher education at least that it's a big change.
Yeah, you mentioned that the amount of parameters in a model, let's say 500 million.
Yeah.
That's how the neurons, like in the neural network. I don't understand what does that structure look like? Is there a certain amount on each GPU, or how does that work?
So what a neural network is a bunch of nodes, which are basically numbers, and they're connected to other numbers. The way the machine works is that it has a strength of a connection. A neural network, what it is a function that has the node. So when two functions are connected, it has what's called a weight and a bias. These are two numbers associated with the way two numbers are connected. So if I have a number here, as it propagates through the network, the next number will be given by the first number times the weight plus the bias. And you add up all the neurons that connect to the next network. It's a very, very simple function. Just adds up the inputs, makes an output. And the number of those weights and biases is just the number of parameters. So it's a very complicated thing. It's just a function. That's all a neural network is. Function defined by creating in a sort of an iterative way. The next element is determined by the previous element by this simple linear function. And then they usually have a kind of a nonlinear activation function on top of it. That's kind of part of the network architecture. So they're just really numbers. There's just 170 trillion numbers that determine a very, very complicated function. What that function does is take the input, the previous text, and outputs the next word. That's all they do. And they're based on 170 trillion parameters to make it work. But that's all there is to it. Really remarkable how simple these are.
I actually have lots of questions, but let's just take one more burning.
Let's summarize the question. The first question was, how do you train a neural network? How do you give it information that determines what it is? How do you put the inputs to the neural network to adapt? And let me answer that one first. So the way it works is this training data. So I showed, for example, particle physics, we could do all these simulations or pictures of cats and dogs. So you would have a kind of an ensemble set of maybe 100,000 pictures of cats and 100,000 pictures of dogs. And what you do is you want the neural network to be a function that takes a picture, outputs either cat or dog. Right? So it's a binary output, either 0 for cat or 1 for dog. What you do is you say, well, let me just make the function to some random function. It's not going to get it right. So then what I want to do is modify all these 170 trillion parameters in a way so that it gets it right more often. What you do is you use this called the training algorithm to adapt these numbers. So you figure out if I change the number to be smaller, it'd be more likely to get the correct answer. Or if I made it bigger, would it be more likely? If it turns out making it smaller makes it better, it makes it a little bit smaller. So it does that for all 170 parameters and moves them around in this complicated space. It's trained on 4,000 TPUs, which are like three-dimensional tensor processing units. And it does this for 4 months. It makes all these numbers smaller and smaller, training on all these pictures. Eventually, it's very, very accurate. It can almost universally do it. The big question about why this works, but that's the basic idea behind all of neural network. What was the second part of your question?
We're going forward
Yes.
on the assumption that what's coming out.
Oh, right. How do we check? Yes. The question was, how do you know? Well, how do you know anything, right? So how do I know the standard model is correct, right? you come up with tests. And you say, well, this is my hypothesis. If it works, will it be correct? So the way it works in practice with a neural network is you have a training set and a test set, and you train it on this set of cats and dogs, and then you ask, does it work for this cat or this dog? And then you just ask, is it doing the right thing? And that only works if you have a way to test it elsewhere, right? If I know what a cat and a dog is, sometimes it has this superhuman level that's better than us, and then all you can do is ask for it to simplify things and come up with ways to test it itself. And I agree that we're getting to the point where it'll be very hard to tell what these machines are doing. But I should tell you, it's a very active area of machine learning, which is the question of interpretability. How do you know that the machine is doing what you think it's doing? It's a very, very challenging one, in which there's been some progress, but it's not clear that we're gonna win, because when they get smarter than us, we're not be able to.